in between them. So in order to get rid of that, we are moving the telescope a little bit, and then by combining those images, we will be able, in fact, to make the gap disappear. So now it's going to continue for another 3 images that we take like that.
Okay.
And after that, we will increase the exposure time to get to see even more details.
So can you tell us a little bit about the target? What is it that we're actually looking at? So this is a nebula called Thor's Helmet, but what actually is it?
Yeah, so this target here is in fact located in the Canis Majoris constellation that you can see here. So this constellation in fact is very well known because it is harboring Sirius, which is the brightest star in the night sky. And this object is very in this same constellation. And what it is, in fact, it is gas which has been ejected by a very massive star, a star that we call, in fact, a Wolf-Rayet star. And those stars, they are about 20 times more massive than our own sun, and they have a very short life, but they have a very dramatic life as well. And so what happens here is that this star is almost at the end of her life, and is now shredding a huge quantity of material. This material is moving at incredible speed of about 500,000 kilometers per hour, so it's really amazing. And this gas is then, in fact, hitting the surrounding material. Here. And because here we have below, we have, in fact, a Ugla cloud, which is a neutral gas, in which, in fact, new stars are being born. So what we see here is a very massive star, which is at the end of its life, is going to explode in a few million years. It's going to explode as a supernova, so it's going to be very bright. And it is now ejecting this material, and this material is hitting this molecular cloud in which stars are being born. So this is really a stellar nursery that we are looking at.
Okay, thanks very much for that. So, can you tell us a little bit more about the other instruments that are on the telescope that you're using right now?
Yeah, so here on UT1 we have for the moment 2 instruments. So we have FORCE, which is really a workhorse because we can do many different things. We can do incredible images, as you can see, but we can also do what we call spectroscopy. We can also use another instrument on UT1, and in this case it is what we call CRIRES. And CRIRES is in fact a spectrograph, very high resolution, but it is observing in the infrared. So those are the 2 different instruments we have on this telescope. For example, at the beginning of the night, I was using CRIRES to observe a comet and to try to detect some specific gas from this comet using this unique instrument CRIRES. And then the second part of the night, we moved with Brigitte to FORCE in order to take images of this incredible nebula.
Okay, thanks very much for that. So, while we're waiting for the observations to complete now, we can't actually show you the inside of the dome and show you the telescope itself because it's still dark and the observations are still ongoing. But we do have some time-lapse video from a night of observations that we recorded earlier. And we can have a look at that now and watch that while we hear more from Paranal about what's happening there and how the observations are progressing. And in fact, I'd like to ask Brigitte about her impressions now, from her first impressions from Paranal. So, how's it all been for you, Brigitte?
It's been amazing. You know, I've been watching videos about Paranal and ESO and everything, but I still couldn't believe my eyes when I arrived at the residential and afterwards at the VLT platform. It's impressive. I mean, ESO had great vision when they built that. There's no words for that actually. You have to see it, you have to be here, and you have to, you know, to feel it and to enjoy it. Looking outside and seeing these telescopes move, and it's great.
So did you get a chance to talk to some of the people up there at Paranal that work there?
Yes, of course. Mathieu took me about everywhere, I think, in different workshops, and also in the control room when we talked to Henri yesterday. A few hours, I think. And yes, to many people. And what's amazing is that everyone is very passionate about their work, and you know, very open, very willing to discuss everything. And with someone who's not an astronomer, I mean, I'm just discovering all that, and it's very interesting. Yeah.
Excellent. So I'm glad you're enjoying it. So Henri, how are the observations coming along? Are they progressing?
Yeah, so now we have started, in fact, a longer exposure, so hopefully we can see even more details, and of course the whole idea is to combine all of them in order to make, at the end, an incredible picture. So here we have not, before what you see here was only 30 seconds, so now we are doing exposure which will be 3 minutes long. But that's why, I mean, you really have to imagine, I mean, this is 30 seconds exposure time, and it's only the power of the VLT which allows you to see this amazing amount of detail in just 30 seconds of exposure time. This is really incredible. So now we are waiting for another minute or so, and then we will have the first of the longer exposure, and then we can see what's the difference.
So can you just explain something? So the image that we just saw on the screen that you have on the computer screen in front of you, you mentioned that this was taken in the so-called H-alpha filter, so that is essentially a monochrome image, but usually the images that the public gets to see are very colorful. So how does that work together? How do the images become so colorful in the end?
Yeah, so in astronomy what we do is that we are observing through a given filter. So in this case it is H-alpha, so we are really looking specifically at hydrogen, which is very hot, and the idea is that we also know at which wavelengths this is going to emit. So for example, H-alpha, we know that this is more in the red. So what we will do then is that when we will have all these images, we will attribute the color red to this filter. Then we are going to take images in different other filters, in the blue, in the green, and in also the red. And we attribute then one color to each of those images, and by combining them, we get the wonderful ESO color images.
So you're sitting there in yeah, go ahead.
Sorry, we just see, sorry to interrupt you, but the first image, long exposure is coming out, and it's really, wow, it's stunning. I mean, it's really amazing to see this. So let's just, I hope you can see it like we see. Maybe you should zoom. Let's zoom the video. So no, that's the wrong. That's the right one. So I mean, there is an amazing amount of detail that we see there. So I can guarantee you that the final image that we will get after combining all those monochrome images is going to be stunning. That's a guarantee.
Yeah, they look really great. So you're sitting there in one corner of the VLT control room, and from there you're controlling the one telescope, the one of the 4 telescopes that make up the VLT. So can you tell us a little bit more about the rest of the facility and the rest of the control room and the other 3 telescopes?
Yeah, so the VLT is in fact 4 telescopes. So it is 4 telescopes of 8.20 meters each. Here we are at Antu, which is UT1. Antu means the sun in Mapuche language. And we have UT2, UT3, UT4. Each of them are also 8 meters, and each of them has 3 instruments to study the sky. So this is really the power of the VLT, is that we have a total of 11 instruments to study the sky, which means that if an astronomer has an idea or needs to study a given object in a given way, he is guaranteed that he will find the right instrument at the VLT. So this is really the power of this wonderful science machine, in fact. In addition to those 4 big telescopes, giant telescopes, we have 4 smaller telescopes, which we call the auxiliary telescopes, which are 1.8 meters in diameter, which is still big, but we call them small compared to the giant telescopes of the VLT. And